Hello. It's so nice to be back. I hope that the clouds didn't come in and you guys actually got a chance to do some stargazing and actually see something. Okay, good. Well, welcome to the Watson Lectures. If this is your first time here, you are joining a community of curious, science-interested people that are participating in a 100-year-old tradition of sharing Caltech's science with the public. And I am your host, Dr. Crystal Dilworth. I am a neuroscientist, a science communicator, and a Caltech alum. Yeah, that's why I'm here, right? But I love being able to share our legacy of science and innovation at Caltech with the rest of the community. And so I'm very honored to be here hosting the lectures for you guys. So I did my PhD here, some of you might know, in the early 2010s, which is like a really interesting time to be on campus because the role of science and scientists in society was kind of undergoing a transformation. We had technology that was driving things, like next-gen sequencing, which was revolutionizing biotech. And we had scientists at the Large Hadron Collider that like deep in the search for the Higgs boson, if you guys remember that. And social media was bringing whole worlds of niche interests into the palm of our hand. And it was allowing a window into the function of the ivory tower and what happened in science and what happened in engineering that people hadn't had before. And this was a very exciting but interesting time because the cultural identity of scientists were going from Revenge of the Nerds to the red carpet. And the Curiosity team actually walked a few of those red carpets. So, in this cultural moment of TED Talks and Big Bang Theory and Bill Nye the Science Guy and YouTube, NASA landed the Curiosity rover on Mars. It was a really big deal. Science was cool. I mean, Twitter and social media made the rover itself a celebrity. I mean, I bet some of you actually followed @Curiosity Rover on Twitter and were, thank you. I guess I see a few back there. And I think this was a first at least for a Caltech robot. And one of the really interesting things about JPL is that some of us know, that this was a research outpost of Caltech, like long before the National Aeronautical Space and NASA, I always forget, Aeronautics and Space Administration, right? Did I get it? Okay. Before NASA was even formed. That was like 1958 or something like that. And the legend of JPL's origin goes something like this. Students at Caltech who were interested in propulsion were experimenting with controlled detonations and small explosions. And they were disturbing the Pasadena neighbors surrounding campus. You people. And you called and you complained and you had concerns about things like noise and danger. And so then President Robert Millikan decided he could solve this problem. He said, all right, all the researchers, we love it. We love what you're doing. Go to the hills of Arroyo Seco. They are uninhabited. You can't bother anyone over there. And they're still there today. That's JPL. Since then, JPL has made incredible contributions and done absolutely pioneering work in terms of contributing to how we understand and what we understand about the universe. And it's way too long for me to go through the entire history in this introduction, so I will say that today, Caltech manages JPL for NASA, and we have a very collaborative relationship. JPL leads the world in technical development, robotics, and planetary exploration. And the Curiosity mission is just one of so many pioneering missions that originated and launched from JPL. Tonight's speaker is a project scientist for MSL, Ashwin Vasavada, and he's going to share with us a little bit about what we've learned since Curiosity landed, and also what we are still learning. This is an ongoing mission, you know, and he gets to see all the science first, so we get to hear about it from him. Before his talk, we'll hear a short introduction by the Associate Director of Flight Projects and Mission Success, very many successful missions. Then you'll see a short video, and then after the talk, you guys get to ask your questions. So what you're gonna do is a QR code will appear on the screen. You'll take a picture of it. It'll take you to Slido. You can upload all of your questions that you have for our speaker. It'll come to me on the iPad. I will get through as many as I possibly can. Please note that questions are usually posed in the form of a question. They are short, and they have question marks. Okay. I just thought this audience might need to know. All right, well, that's plenty from me. So if you would please silence your phones, your watches, all of your tech that makes noise, note your nearest exit, and help me welcome to the stage JPL's Associate Director for Flight Projects and Mission Success, Kir Patel.
Thank you, Crystal, for that great introduction about JPL and Caltech. Good evening and welcome. It's my privilege to introduce an exceptional JPL planetary scientist and someone who has helped shape our understanding of Mars, Ashwin Vasavada. I've known Ashwin since the late 80s, early 90s, when we were young'uns working on Mars Observer, and have crossed paths after that, and again when he was on MSL and I was on the planetary directorate at JPL. Ashwin right now is the project scientist for the Mars Curiosity rover, which has been investigating the red planet, ancient past, for the last 13 years. You'll hear more about the mission and the rover shortly, so I'd like to focus my remarks on Ashwin himself, and why his work is so meaningful to JPL and the world. Ashwin's not only a passionate scientist, he's an extraordinary leader and communicator. He leads a global team of 500, imagine that, 500 scientists all over the world. And when I mean all over the world, Europe, Russia, name the continent, he probably has a scientist on it, working on it. And he deals with them on a daily basis to chart Curiosity's path and maximize its science returns. The other thing he has, which is very hard to find with engineers and scientists, he's a very, very gifted communicator. You know, through interviews, podcasts, talks like this one, he regularly shares the wonders of science and space with the world, helping us feel more connected to places millions of miles away. And Ashwin, no pun intended, leads with curiosity. His work brings us closer to answering one of humanity's biggest questions: are we alone? We're fortunate to have him guiding this iconic mission and expanding our knowledge of our planetary neighborhood. And now, please enjoy a short video about his journey, and thank you and enjoy the evening.
As I was growing up, I always had an interest in space, and a lot of that came from NOVA specials and things like that.
Vikings to Mars and the search for life there.
I had a book that had a picture of Mars taken by the Viking lander. It captured its own antenna, beaming back the signal to Earth, and this barren, rocky world out in the distance. I could just stare at that picture for hours because it just brought home the fact that you could send these robots out as your emissaries. And it was just sitting there lonely on this planet, beaming back this data to Earth. And we were all anxious for anything it could tell us. I'm Ashwin Vasavada. I'm the project scientist for the Mars Science Laboratory mission at JPL with its Curiosity rover. And that means that I help lead the team of over 500 scientists around the world who are making discoveries with our rover. I grew up loving space, but really not having an idea of how to pursue the career. So I actually applied as an aerospace engineer to university, kind of had the word space in it, sounded right, and quickly realized that my passion was not in the engineering of things, but more in understanding nature, understanding how the world worked. I got into Caltech with the idea that I'd be working on a spacecraft called Mars Observer.
And liftoff of the Titan III rocket with the Mars Observer and America's return to the Red Planet.
As I was driving down to Caltech, I was listening to the news and heard that the spacecraft was lost.
Somewhere in space tonight, Observer remains silent, possibly dashed the hopes of hundreds of scientists who've spent years on the project.
My advisor here, Dr. Andy Ingersoll, who just so wonderful to work with, he said, well, I'm working on this thing at Jupiter. And that was life-changing, you know, getting to work with an actual mission on it, with a spacecraft team. As a grad student, I worked in the sub basement of one of these buildings, you know, windowless office. But I would go there sometimes at midnight or 2 a.m. when the latest batch of images would come down from Jupiter. And I would sit there and look at the monitor and think, I'm the only person on Earth who's ever seen these pictures. You know, they will tomorrow morning, but I'm looking at them now as they've just arrived. Now I get to do that almost every day on Mars. The scariest moments of the mission really were launching it, because I was standing there and I saw this basically controlled explosion, you know, with our precious rover on the top of it. And then landing, you know, the famous 7 minutes of terror, where all these incredible engineering feats had to all work perfectly for Curiosity to safely land on the surface. Entering the atmosphere with a heat shield and parachute coming off, and the rover dropping out of the aeroshell wearing this rocket jetpack and flying its way down to the surface. When it did land successfully, there are those, you know, now famous pictures of all of our engineers jumping up and down, some of them crying. I was in the room looking at them, but not with them. So of course my mom wanted to know why I wasn't on TV. It's really a great experience to every day get into work and be around this talented group of engineers who know in and out how to operate our rover safely, look at the screen together, point at rocks, and together we figure out how to get to where the science team wants to go in a safe and efficient way. Exploration and scientific discovery provide this inspiration. They provide this moment for people to think a little bit of bigger picture for a second. We still don't know whether we're alone in the universe. It's incredible to be part of the ability to answer that question. Fantastic. Oh, a little overwhelming, actually. Thank you all for coming here tonight, and thank you for everyone involved in putting on the Watson Lectures. What an experience, what a great evening already. So I'm Ashwin, and this is the real star of the show, I assure you, the Curiosity rover. It's a car-sized rover that's been on Mars now for 13 years. We started developing it in the early 2000s. It landed in 2012, and we've been operating it ever since. And you know, as you heard, it's still going strong. It was designed to last just for a few years, but now we're on year 13, going on 14. You may have heard more recently about the Perseverance rover. Perseverance looks a lot like Curiosity. It's actually its younger sibling. So Curiosity arrived, as I mentioned, in 2012, and it's still going, and happy to tell you a little bit, well, a lot more about it tonight. So as you saw in the video, August 5th, 2012 was a night of pure joy for us who had worked over a decade to put the rover together. It's always be a highlight of our lives and one of the greatest accomplishments of our careers. And the emotions that came out that night weren't just because of the safe landing. The landing was a culmination of a decade of incredibly intense work to design, to build, and to test the rover, and of course, this fantastic landing system that you saw. Curiosity was the most sophisticated spacecraft JPL had ever built at the time. And getting it to the launch pad used everything that JPL had learned over 50 years of exploring the solar system for its mechanical design, its avionics, its thermal system, its propulsion, and the 3.5 million lines of code in its flight software. Getting to the Curiosity to the launch pad also required several new inventions, like a car-sized, long-lived, nuclear-powered rover, and a new way of landing a spacecraft that was much larger and 5 times as heavy as anything we'd ever landed on Mars before. It was by far the most ambitious and difficult thing JPL had ever done, requiring hundreds of people, many working 3 shifts, 24 hours a day, for months at a time. Curiosity's landing was also a cultural phenomenon. Millions of people, including many of you, probably held their breath as Curiosity landed and celebrated what was perceived not just as a triumph for JPL, but as a triumph shared by humanity. And for me and my fellow scientists, landing night was also the moment that the engineers who had labored so hard to get Curiosity to Mars would turn over the keys to us as the science team. And I remember walking back to my office that night after celebrating the landing with the team, and just feeling like there was this giant spotlight that had been on the engineering team for not only this evening, but the decade, and it was shifting over to the science team. And NASA and the world would be waiting to see if what we discovered was worthy of all it took to get this rover to Mars. So a little bit of pressure. And that's what we'll talk about tonight. I'm first going to share with you what Curiosity was designed to do, and then we'll follow Curiosity's journey up a Martian mountain, and we'll see some of the discoveries that we made. And we'll also talk about some of the challenges that we faced after landing on Mars as we were making these discoveries. So let's begin talking about what Curiosity was designed to do and what its place is in the history of Mars exploration. For 100 years or so, people dreamed about intelligent civilizations on Mars. And you can imagine that when Mariner 4 first flew by Mars in 1965 and got the picture in the upper left there was a sense of disappointment because the pictures really just showed Mars to be a cratered surface a lot like the moon. But it wasn't long before we followed that up with other spacecraft that started revealing that there's rivers running between the craters on the plains that you see there. And then on the far right, you see an intricate form, which is a river delta, where a river once flowed on the surface of Mars and emptied out into a standing lake. And images were these, reignited the excitement about Mars. And they were really important scientifically, too, because it was the first actual scientific foundation for thinking that life may have been possible on Mars, at least in its ancient past. So NASA began to intensely study Mars and used kind of a step-by-step approach. Ultimately, we wanted to understand whether life originated on Mars. But that was actually too challenging to do at the time we were doing it a few decades ago. It's really hard to design a robotic way of answering a question about whether evidence of life is present in a rock, especially if that was 3 or 4 billion years ago when that rock captured that evidence. So instead we started with this question over here: Did Mars have persistent liquid water? And we mapped Mars in great detail with satellites and sent initial rovers to Mars. And we found overwhelming evidence that water had flowed on the surface of Mars in the ancient past. And with that in hand, the scientific community determined that a robotic spacecraft could be designed to answer a more comprehensive question about the possibility of life. And this was the question assigned to Curiosity. Was Mars ever a habitable planet? Yeah, so what does that mean? So what makes a place habitable? Well, you can go to places like this on Earth that don't look very hospitable to life, but life is teeming there, and you can study, based on everything we know about life on Earth, what life requires. And it requires a few things. It requires long-lived liquid water. It requires key chemical elements, organic molecules, basically the raw materials of life. You need sources of energy to keep life going. So sunlight's always there, but even deep underground on Earth, microbes have learned how to use chemical energy from rocks and soils. We can look for that on Mars. And we need to find a place that has all these things, but also lacks extremes in things like temperature, acidity, salinity, and radiation that could be harmful to life. So with that list, you can see there's no one measurement we can make with a spacecraft that tells us whether a place is habitable. We actually have to make a whole lot of measurements and integrate them together to form a picture of habitability. And so to do this, Curiosity was equipped with two of the most basic general instruments you'd find in every geological laboratory on Earth, which is one, a mass spectrometer, tells you all the different chemical elements and molecules that are around, and an X-ray diffractometer to tell you exactly what minerals are present. And minerals that you can find in rocks are special because they capture what the environment was like when the mineral formed. The difference between graphite and a diamond tells you that even though they're made out of the exact same thing, one of them was exposed to a much different environment than the other. And so by measuring chemicals and minerals, we could unravel the habitability of an ancient environment. These instruments also analyze samples of rock, though, so Curiosity would have to feed them, and it did this by having a jackhammer drill at the end of a 7-foot robotic arm that could bore into rocks, capture powder from those rocks, and feed these instruments with samples of rocks over and over again, all 100 million miles away, without ever being able to clean the instruments or anything like that, at least with a human. So very sophisticated designs, careful designs to be able to equip the rover with those laboratories. The fact that we had these relatively big laboratories and a 7-foot robotic arm also determined the size of Curiosity. You can see how big the rover is on the right there, and Perseverance as well, compared to the other rovers in our JPL rover family tree here that have been sent to Mars before. So now we have a goal for the rover, understand the habitability of Mars. We have a payload, but we still need to figure out where to send it. And you can only send it to one place. So the next challenge we had as a science team was figuring out where's the one place you could send this rover on a planet that is the size of all the continents on Earth put together, that you could best answer this question of whether Mars ever was a habitable planet. And to make things harder, we didn't want to find a site that would tell us about whether Mars was habitable today. It's less likely than the fact that it probably was much more habitable 3 to 4 billion years ago, when maybe the planet looked like this. May have had standing bodies of water, rivers, lakes, maybe even an ocean, and a lot more precipitation, all the things that would help it have been a habitable planet. So after about a 5-year search, we've settled on this place. This is Gale Crater. It's about 100 miles across. And what makes this place really special, as any geologist will tell you, a history of a planet is recorded in its rocks, and particularly sedimentary rocks. Rocks that form as sediment is brought in by wind and water, and the sediment that's brought in by wind or water forms stacks of layers that go from oldest to youngest. And by studying those layers, you can sort of read the history of a planet like a book. And so we could go to this place that had this 3-kilometer high stack of sedimentary rock in it, send a rover, climb that mountain, and understand what the history was like, era by era, 3 to 4 billion years ago. So we got to Mars. No spoiler there. You already know we got there. So this is the picture from day 23, just showing you. We had to land sort of off of the mountain for safety reasons, but we could tell, even from satellite data, that the layers of the mountain that you see there at the top varied in their mineralogy as well. So There were some layers that were enriched in hematite, which is an iron oxide. There were some layers enriched in clay minerals, and others enriched in salty sulfate minerals. And what was exciting is that all of these three types of minerals form when water is interacting with the basaltic rocks that Mars was originally made from. So this gave us some hope that this giant stack of sediments wasn't just all blown in by wind, but water was involved as well. And the goal was to send this rover to this mountain, climb it, and explore each one of these ancient wet environments to see if any of them had all the ingredients we needed to call it a habitable environment. There was another exciting aspect about Gale Crater 2. The clays going into sulfates, the kind of saltier minerals, is something that you can see widespread over Mars. And we had a hypothesis as a scientific community that this actually was a record of Mars climate change that took it from the warmer and wetter planet a few billion years ago into the colder, dry planet it's been for the last few billion years. So this stacking of clay minerals, which require much more water to interact with the rock than the salty minerals, which may have formed in drying, evaporating lakes, for example, would be a climate record that we could study with the rover too. So we had two ambitious goals for this mission. The primary one being to understand the habitability of Mars in its ancient past, and the second, to understand whether we could learn something about this major climate transition and learn something fundamental about Mars's climate. So we landed at this place called Bradbury Landing, and the first thing we did, we wanted to drive actually up to the mountain, that valley there, where we eventually reached, but we drove the opposite direction for the first bit of the mission. I'm going to turn on my laser pointer. There you go. So yeah, we landed here, drove this way, because Yellowknife Bay was an area that we saw from satellite images. It looked like there was a fan of material spreading across the crater floor, and a river might have flowed down from the crater rim. So we really wanted to see if even on the crater plains, before we got to the mountain, there might have been an ancient river and lake system. As we drove across it, we got this spectacular view. Looks like kind of an upturned sidewalk that's falling apart, but it actually is a rock called a conglomerate, a rock made of a bunch of other smaller rocks that had been cemented together, and it's now eroding, and the rocks that are coming out of it are rounded pebbles. And as we all know from our experience on Earth, one of the ways you get rounded pebbles is by having them be transported in the bottom of a river. And by comparing how round these pebbles are with our familiarity with rivers on Earth, we could figure out these pebbles were transported by several miles in a stream. And I can tell you, it's one thing as a scientist to see satellite pictures of Mars with rivers that I showed you earlier. It's a whole other thing to be on the ground on Mars and actually know that you're driving through an ancient riverbed. And this is the first time we'd ever seen that on Mars' surface before. So we followed the riverbed, so to speak, and we went to where we thought might be a place where there might have been a lake on the crater plains. And when we got there, we saw this view of Mars that really looked unlike any picture of Mars we'd seen before. Usually it's just a bunch of rocks and boulders. But here you had this beautiful, flat, smooth surface that really looks like a dry lake bed might look in the desert, on Earth today. And this was a place that we did our first big experiments. We took out that big arm, we took out that drill, drilled into rocks, fed it to our laboratory instruments. And of course, our geologists studied whether this really was a lake bed. And what we found is a lot of fine-grained, finely layered rock. It was clay-rich rock, so water had interacted with the basaltic rocks and turned some of the minerals in those rocks into clay. Our laboratory instruments found that the water that was once present in this lake was not, had a neutral pH, so it wasn't too acidic, wasn't too alkaline, didn't have too much salt in it. All good news for any microbes that might have been living there or wanted to live there in the ancient past. We found carbon and hydrogen and nitrogen and oxygen and phosphorus and sulfur, all the basic elements that life requires to do its machinery. And we even found organic molecules, collections of those elements containing carbon and hydrogen and oxygen and nitrogen. Very small organic molecules, not as sophisticated as the amino acids and proteins in our bodies, but fragments that could have been once those larger molecules. But of course, we're drilling into rocks that had been exposed to radiation and Mars environment for a few billion years. But This satisfied exactly what we were looking for. So even before we reached the mountain, we found an area on Mars that, at least for a moment in time when this lake was here, was an ancient habitable environment. A microbe would have been able to live, we believe, in this lake. We couldn't prove that it ever did. This payload isn't capable of doing that. We really need to bring rocks back to Earth and study them to figure that out. But life was possible here. Next thing we wanted to do was drive to the center of the crater, to the mountain, of course. We think maybe this is what it might have looked like a few billion years ago, where here's that river coming down from the crater wall. We may have seen some of the stream bed deposits here in that conglomerate. We saw an ephemeral lake, but our hypothesis was that all of the mountain itself, all of Mount Sharp, may have been slowly built up over time as lakes filled the crater for long periods of time, stacks of layers, and then eventually eroded back into the shape of a mountain. So our hypothesis was, as we continued to drive on, we'd see some of these deltas where the rivers emptied out into water, and then we'd see lake deposits at the base of Mount Sharp. So you can imagine how exciting it was, and we just drove continuously for a year, trying to get as fast as possible to the mountain. And that's when we ran into our first big challenge. Some of you may know about our famous wheel situation, but we have these aluminum wheels, and we started seeing daylight through them, and that's not supposed to happen. And we pride ourselves on being good engineers, and so my gosh, did we design these wheels wrong? Did we not make them thick enough to withstand, to hold the weight of the rover against sharp rocks? Surely we thought of all this, and we did. But you can see the rocks we were up against, not very friendly, especially out on the plains. And you can also see, though, in our defense, that the wheel is doing a pretty good job of holding the weight of the rover up on that rock. The rock isn't punching through. So what was going on here? And it took a lot of work by our engineering team to figure out that what we hadn't thought of was how our suspension system interacts and how we were driving the wheels, such that when we were driving the wheels all at the same rate, if one wheel had to go up and over a big sharp rock like this, the other wheels would sort of drag it into that rock and add a little bit more force and cause the aluminum to tear. So, bummer that we did not think of that. But the good news is our engineering team was able to reprogram the flight software of the rover to add a feature that's sort of like the traction control button in your car, where every wheel can rotate a little bit independently. And if one wheel has to go over an obstacle, it can do that. And that actually has preserved the wheels. We also did a lot of testing. We made this torture track at JPL and ran the wheels like 50 miles or something crazy like that. And our best geologists would come up with the worst rocks to put on this torture track. And the reason we do this is because testing like this, if you do it well and you have confidence in the test that you're doing, it gives you the confidence to then go forward on Mars and be concerned at the right amount. In other words, the worst thing we could have done at this point is say, we're never going to reach the mountain, it's too dangerous, we want our wheels to last. But now we know, after all this testing, exactly how long our wheels will last, based on the terrain that we're seeing. And fortunately, it was enough to take us to the mountain. And obviously, 13 years later, our wheels are still, they kind of look like, some of them look like that middle one, I'll be honest. but we're doing fine. We also did a lot of work rerouting the rover. From the geology point of view, we looked at maps of the surface and found where the smoothest places where we could drive, that we could still accomplish our science. In this particular example, I voted for the green path, but I didn't win. We decided to take this pink path up here, and it was great. It was a great path, had a lot of good science on it. All we needed to do was get through this little valley right here. You can see there's a mountain there, or a little hill here, a little hill there. We had to get through this. How hard could that be? We got there, and there was a 5-foot wall of sand blocking the way. So these are the challenges you can run into on Mars. But fortunately, when you have a giant car-sized rover, we made pretty quick work of it. So that was great. And we could continue on then. We could look for those deltas as we got closer to the mountain and look for those lake sediments. And I think one of our more spectacular pictures is this formation of tilted beds of sandstone. So as rivers move fast, they can carry particles like pebbles or sand, and when they hit a standing body of water, the water slows down and the larger pebbles and sand fall out, and you create these sandstone delta deposits. And they're all sort of tilting towards the center of the crater, telling us to go forward to where the lakes would be. And we got to the mountain, and the entire base of the mountain was formed by these finely layered, fine-grained sediments, clay-rich sediments, exactly what you'd expect if, every year on Mars in the ancient past, a pulse of water came in, rivers delivered a new layer of sediment to the interior of the crater, and only the finest grained, silty stuff, made it past the deltas and settled out into the lakes. And every one of these layers may represent kind of an annual cycle. And as we climbed the first, few hundred meters of vertically on this mountain, we continue to see these millimeter scale layers. And we saw probably about 200,000 of these layers. And so even if you just take a simple mathematical view that if they're annual cycles, this would be 200,000 years, probably a lot longer. This tells us that these lakes persisted that long in Gale Crater. And when you get into hundreds of thousands of years and millions of years, you're actually talking about timescales that evolution and life could have made use of. So this is much more, is as exciting, but actually even much more exciting than that lake at Yellowknife Bay on the plains that may have only been there for a few hundred years. Here we have a record of lakes that lasted probably hundreds of thousands, if not millions or tens of millions of years. This is how we drill. So we're having a great time drilling as we're climbing the mountain. We put the arm down on the ground. There are these two stabilizer posts. So we first put the posts on the ground. We press the arm really hard against the ground. And then we have a motor called the drill feed that moves the drill back and forth. So it's sort of like operating a drill press. If you ever do that in your garage or something, it's a very controlled, safe way of drilling where you're stabilized against the rock and you drill up and down. And why am I telling you all this? You'll see. So yeah, this is where we were in about 2016, having encountered the foothills of the mountain here at Prump Hills and climbing up a few hundred meters and finding all this evidence for the lake sediments. And we were right at the precipice of getting to our second major goal of the mission, to reach these layers that we saw from space that had these minerals that form when water interacts with rock. So even though we'd seen now clay minerals and lakes before, they weren't actually visible on the satellite data. We didn't expect to find them so early. But now we were going to get to the mother lode, where we saw things even from space before we landed. So we're right about here, about to get to this clay sulfate transition where we could also understand the climate change of ancient Mars. And we had our drill disaster, our second big challenge of the mission. So the kind of ironic thing is we actually named this drill hole Precipice, and not intentionally, that just worked out funny that way. And when we tried to drill Precipice, we commanded the drill, like we've done now 15 times or so at this point in the mission, and we got in the next day to see the telemetry that had come back, and the arm was loaded against the rock, but the drill feed never moved. And it's always, things happen, glitches happen. So the first time you get the report that something failed to execute the way you intended, your heart drops a little, but you're like, they'll figure it out, it's fine, And usually that's what happens. 24 hours later, it's a distant memory. But this time, we tried to move it, didn't move, tried again and again and again. And all that we could do, we found that if we moved it just the right way and turned the brakes on and off like 5 times and spun it around in a circle and whatever, we could get the motor to move just a little bit, a fraction of a millimeter every time we commanded it. So we actually did that for months. We commanded the feed to move, And we got it beyond those stabilizers, and that's the big deal, because if we never got the feed beyond those stabilizers, we could never get the drill bit to touch Mars ever again. So this was victory number one, just getting the drill feed beyond the stabilizers so the drill bit, which is right here, could touch Mars. But it's only step one, because we never designed this rover to be able to drill like freehand, like you would with a drill if you're drilling a hole in your wall at home. We had to figure out if the arm would even survive the forces needed to press it by itself to control that drill. And what if the drill wobbled around? Would we snap a joint in the arm? None of this was how we intended to drill on Mars. And fortunately, we have a test bed on Earth. It's a full-size model of the rover with a very flight-like arm and drill. So this is what it looks like in our shed at JPL. And we did 1.5 years of testing and analysis and reprogramming the rover's software in order to teach it 100 million miles away how to freehand drill on Mars. And this is one of our tests. So I'll run that again. But as you see it freehand drilling, here are the stabilizer posts, no longer touching anything. You can see it wobbles a little bit. Yeah, and the fear is that as you're drilling and you start to shift over to one side, it can really put a lot of side stresses on the arm. And our arms, we're not going to ever snap our arm because we have nerves that tell us that we're forcing things too much. And robotic arms have a nervous system too. It's just we designed this one to have sensors just where we needed them to do the stabilized drilling. So we had to make sure we could sort of re-understand and measure the forces needed to prevent, bad things from happening with this freehand drilling. And we got it to work. But even that was not the end, because we normally would drill, this feed would come out, and then we would retract the drill, and we would collect material in this bit right here, and it would flow out into a sampling system that's over here, where we would sieve it to make sure we got all the shards and big chunks of rock out and only delivered the finest grained stuff to the instruments for safety reasons. And we could portion it because we wanted to deliver a very precise amount of material to the instruments. So, after we had spent months coaxing this motor to get out beyond the feed, there's no way we're moving it back again. And so we also had to figure out how to deliver the sample to the instruments in a brand new way. And this actually we did about the simplest thing you could imagine, which is we just put the drill over the lid that covers the instruments and rotated the drill backwards, and stuff fell out. And of course, we tested this over and over in the lab. We got, there's a lot of luck involved beyond just the amazing skill of the engineers that I get to work with. The luck being that this drill wasn't designed to do this, but it just fortunately drilled a very consistent fine powder. So the sieving was probably a belt and suspenders thing anyway. So it was safe to deliver it without sieving. And we actually learned how to rotate the drill backward just the right amount, like a half a second, so that we got the perfect portion size to come out. So that's that. Believe me, lost a lot of sleep for this 1.5 years. And this is our first successful freehand drilling on Mars. Yeah. This is how proud the rover is. Looking at its first freehand hole here. I also love this picture because the lighting is so awesome. This was actually taken at the final stages of a global dust storm. And so there's a huge amount of dust in the atmosphere blocking the sun, and you get this gorgeous diffuse light for this portrait. So we had drilled this many holes before the drill had its issues. We've now drilled this many as we've continued to climb up. So most of what we've done now is in this post-drill disaster era. And a lot of our big discoveries have come in this era as well. This is our library of all the different organic molecules that we've discovered with Curiosity. And they're still small. If anyone's taken organic chemistry and seen what kind of organic molecules that are in our bodies, these are all pretty small. but they're big enough and they're diverse enough that we're actually able to sort of make educated predictions. I didn't want to call them guesses, but predictions about what originally might have been present on Mars before radiation and water, groundwater and other things degraded the organics into what we can find a few billion years later. So we can look at the precise sort of types of molecules that we see and invert what might have actually been there. And one of these long chain 12 carbon atom molecules, the arrangement that we saw tells us there were probably molecules called carboxylic acids on Mars that degraded into these, and those carboxylic acids are the building blocks of things like amino acids. So we're a few steps away of the things that are really the building blocks of life, but we have evidence that they may have existed there in these lakes on Mars in this crater. So we actually then, of course, finally got to the clay unit and the sulfate unit as well. You can see how different the rocks are when you go from the clay-bearing rocks, which are very soft and very highly degraded basaltic rocks with all the clays that have formed in them, into the sulfate-bearing rocks. And while we could see this mineral transition from orbit, we couldn't, from orbit, really confirm that it represented this change in the ancient environment from wet to dry. For that, you really need to do the geology, the sedimentology. So these clay-bearing rocks all were these fine-grained, finely layered rocks, clay-rich rocks that would form from silt in lakes. And the sulfate-bearing rocks turned out to be coarse sand that was arranged in not flat layers, but very nice wavy layers where ancient dunes had once existed and then hardened into rock. So there was now a geological confirmation of this hypothesis that lakes were once present and then the environment dried, and from that point on, only you'll see maybe not always from that point on, but for the most part, Mars was pretty warm and dry after that, and sand dunes would go across the surface and would be left hardened into rock for us to find all this time later. But as we were driving through what should have been the dry era on Mars, we occasionally got surprises. This is 2023 now, so we're catching up to the present here. This is a really bizarre layer. So we could see this continuous layer of dark resistant rock from orbit, and we were eager to figure out what it actually was. We got there, and it kind of looks like one of those ropey lava flows that you might see on a volcano in Hawaii, but there's no volcanoes in this area, and it just didn't make sense for there to be a single lava flow like this. And we looked at the outcrop here where it was eroding from being a continuous layer. We saw a bit of waviness in it, got us a little excited. And when we drove on top of it, we found really what it was. It actually was an ancient lake bed that had just hardened into rocks based on the minerals that were present in that lake. And we saw wave ripples preserved for us for the first time. And these were the kind of ripples that would form in a shallow lake when wind was blowing on Mars and waves were forming on the water of that lake and jostling the sediment maybe 5 feet below the surface and creating these beautiful symmetric ripples. And you can find ripples preserved in rocks all over the Earth. And it actually was a little surprising why we had never seen them on Mars, even though we had all this other evidence for lakes. And it's possible that it's because it never was really that warm, and maybe all the lakes that we'd seen earlier were covered by ice, and so they couldn't form waves. But what's fascinating about this is actually evidence for a climate that would allow an open body of standing water on Mars, because you had to have the surface open for the wind to blow, the waves to form, which led to the ripples. Last year, we're excited to reach another formation that we'd seen on satellite images, and this is a rendering from satellite images. We saw this kind of sinuous channel cutting across the layers of the sulfate unit. When you see something that's sort of waving across a landscape, we all probably think of rivers and streams, and yet it was cutting across the rocks that formed when Mars was very dry. So this meant that if this was a river, water had reappeared in the drier era of Mars, and probably would be some of the youngest evidence for water that we'd ever see in the mission, since it would have happened not only after, it would have happened after the lakes formed the bottom layers of Mount Sharp, the dunes formed the upper layers, and then those layers were eroded back into the shape of a mountain, which probably took eons itself to do. And then this river flowed and carved its way through these layers. So it could be a relatively young, instead of 3 or 4 billion years old, maybe only 2 billion years old. But that's still pretty young for evidence of water on Mars. And we got there and we saw this incredible channel, now filled with sand, but it's nice as sort of waves of sand. The channel was also just full of debris, all these rocks of different shapes and colors. And that's very typical of what you might see in a fast-flowing river, because it's bringing down debris from higher levels of the mountain. So this is just a collection of debris that we actually studied a lot of the different colors and shapes and textures, because this might be your only chance with the rover to see some of the highest layers of Mount Sharp that have been eroded and washed down for us to study. One real surprise was this patch of very bright white rocks in the middle of the channel. We'd never seen anything like this, both in sort of the brightness of the rocks and a kind of a discrete collection like this. It was the only place we'd ever seen it. And so we were intrigued, and we drove the rover over there, and we got up to one of these rocks, and it has all these holes in it, presumably from how it formed, but then a lot of flutes on it as the wind has eroded it, as it's been sitting on the surface for billions of years. And we put our arm on it, and we figured out that it was made of pure sulfur. And you can see, I've talked a lot about sulfate minerals, which is a form of sulfur, but you can find sulfates and sulfides a lot of places on Earth, but to find pure elemental sulfur is a little bit more rare and unexpected. It forms kind of near volcanoes on Earth, or maybe in hot spring environments, neither of which were anywhere around Gale Crater. And if you've ever seen sulfur near a volcano, you sometimes gets that very bright yellow-greenish color to it. And we drove over one of these rocks with our wheels and revealed this beautiful translucent yellow-green material. So this is one of the more beautiful finds of the mission. And also, I can tell you, we have no explanation for this. So we're still working on why there's a deposit of pure sulfur in the middle of this crater, and we've never seen anything before or after that's close to it. So this is where we are now. I remember on day 23, looking up at the mountain, just, cautious to even dream that we would get there so high up one of these days, and dreaming about what it would be like to have a rover driving through canyons on Mars, with cliffs on either side of you. And it just had nothing like this had ever been done on Mars or any other planet. And it was just almost too much to imagine, but now we get to do that. And these are the kind of views we get as we're high on Mount Sharp, and we've now driven about 37 kilometers, which over 13 years isn't that much, but we stop a lot. we do a lot of science every day along the way, just take incremental steps. And we've actually climbed about 1 kilometer vertically now. Yeah, we're pretty high up. We got some good views behind us. And it's not over yet. We're still going. The rover is getting old. Things are breaking. But we're still able to do the vast majority of all the science that we could do the day we landed. And we're just really fortunate that that's the case. We hope to get to this brand new layer we've never seen before and have no idea what it is, even from satellite images, very little understanding of what it is. But it forms these beautiful tilted layers and cliffs. It reminds me of something you might see in Arizona or Utah. And so hopefully we'll be there in about a year or two. And, our legacy, as I start to wrap up here, is that, we were sent to figure out if we could find a habitable environment on Mars. And we didn't find just one. We found a record of habitable environments that probably lasted millions of years. And the quality of those environments, all the list of things that I mentioned and the number of organic molecules we found, I think far exceeds even our highest hopes for what we might have thought we would find the day we landed. So, it's really incredible, and it motivates what we want to do next, which is to go to Mars and bring back samples to Earth to answer that question finally, did life ever take hold in these wonderful environments that nature created a few billion years ago. But I want to end with another part of our legacy. I don't know, I get emotional when I talk about this next part, so I don't know why. I'm gonna keep going. But another part of our legacy that is really important to me personally, and that's how the people that have come through the mission. We've trained and given an experience to hundreds now of undergraduate students and graduate students and postdocs who've gone on to do great things in planetary science and other fields, but that's another thing that these missions accomplish. It's just been so wonderful to have dozens and dozens of PhD theses all around the world come from our data. And Lauren Edgar here, who was a graduate student at Caltech the day we landed just this year. Yeah, so I can't think of any way better to end that. So I just want to say thank you again.
Ashwin, that's absolutely incredible. And one of the things that I really love about your story that you told is that it really shows, the collaboration between engineering and the scientific team and the way that you're able to work together to solve all of these unforeseen sort of problems. And that's one of the things I think that JPL does so well. These huge, how many people do you think and actually worked on this mission, and how long from its conception to what you're showing now?
Yeah, so JPL is usually around 5,000 people. It kind of varies, but it's estimated that about 1,000 people were working at the peak time when we were putting together Curiosity. 1,000 people at JPL. And if you expand that to other NASA centers and small businesses we work with, probably about 3,000 people.
That contributed to that.
Yeah, that contributed to it. And then we still have 500 scientists on the science team, many of whom have been there as long as I have, for 13 years. Yeah.
As a scientist, I know that when you're reporting on the results of an experiment, it can be quite easy to write the paper in a way that sounds something like, I totally expected this outcome, and this was definitely what we were trying to do when we conceived these experiments, and here's all the amazing things that we totally knew was going to happen. You're showing surprises, unexpected discoveries, absolutely groundbreaking data. How many of these can you get in one mission?
Yeah, it's true. It makes it fun. Yeah, and it's also challenging as a project leader, too, because we have to always continually justify our existence to NASA, which is, I understand why. Taxpayers like you fund our missions. But, we promise them what we're going to do, and then things go all different directions, and we have to tell them, like, for example, honest truth, we said we would be up to the layers much sooner than we ever got to any of those layers. And that's because we kept making discoveries lower down the mountain. So we always had to tell NASA why we're late and show and prove to them that it was worth it. And it really has been worth it.
How long until we get an autonomous vehicle on Mars?
Yeah. So, we have one in the sense that we don't drive Curiosity with like a joystick. Because Mars is up to like 15 or 20 minutes away by the speed of light, we actually command the rover to do a whole drive. Like we use software where we can visualize the terrain in 3D and we can plan out a route for it. And we can drive the rover along that pre-planned route, and we can even drive the rover beyond our pre-planned route because the rover has autonomy on board. It takes three-dimensional pictures of its environment, it recognizes hazards, and it can chart its own path through that. So yeah, we have a self-driving rover on Mars.
All right, it's already autonomous, people.
Yeah.
How are the sites on Mars named? Who gets to name them? Because they're pretty cool.
Yeah, every mission, there's no rules, fortunately, no big rules for small things. For big things like Gale Crater, there's actually an international group that determines what names are appropriate. But for anything small, like the size of a hill or a pebble, it's really the choice of the team. And previous Mars rover missions have chosen like cartoon characters or fun things. We decided that we were going to name everywhere Curiosity goes after geologically important sites on Earth. And so we had the science team choose a lot of different sites, whether it's the United States, like the Grand Canyon area, or Yellowknife Bay in Canada, where some really important geology was done. And then based on that region, we choose all the individual names.
Interesting. Has one of your contributions been selected for a name?
Yeah. Yeah, right. You're right, yeah.
Yeah, I've named something on Mars. Where did the water on Mars go, if it was there?
Where did the water on Mars go? Yeah, good question. Let me know if you find out.
That's what we're trying to figure out.
No, there's some thoughts. So some of the water is in these rocks, like into the clay minerals, for example, bound now forever into the rocks. But largely, there's sort of two questions: where did the water go, and why did the water go? And the why is a lot of the reason. The reason for that is because Mars lost its ancient atmosphere. It had a thicker atmosphere. You need a thicker atmosphere to allow the water to be stable, so it won't just all boil away or evaporate away. And so we think Mars probably had an Earth-like atmosphere in terms of pressure 3 or 4 billion years ago. Today, it only has about 1% the pressure of Earth's atmosphere. And if you were to put water on the surface of, like a cup of water on the surface of Mars today, the pressure is so low, it would like boil away. So we think what happened is that Mars is a small planet, so it cooled faster than the Earth. It used to have a more vigorous magnetic field as the interior of Mars circulated, like Earth still does, and generates a magnetic field. When Mars cooled and that circulation stopped happening and the magnetic field was lost, it allowed the solar wind, the same thing that causes auroras and things on Earth, to strip away the atmosphere. And once you lower the pressure of the atmosphere, the water evaporates and can be lost to space along with all the carbon dioxide in the atmosphere.
You're using words like Earth-like a lot. So how far away are we scientifically from being able to say that's our future? That's what Earth is going to look like in a few billion years.
Yeah, hopefully far. So yeah, it won't. It is interesting though, because the planets do give us a lot of insight that we can't get just from Earth. So for example, the greenhouse effect was discovered on Venus, which has a really thick CO2 carbon dioxide atmosphere, and that generates a lot of heat that warms the surface. Much more dramatic than the little bit of heat it generates on Earth, which is in itself pretty dangerous. And Mars in the same way. You can sort of look at the other end of the spectrum. Venus kind of went one direction, got a hugely thick atmosphere. Mars lost its atmosphere.
Cassini, Curiosity, pretty huge, iconic missions. Do you have advice for either aspiring scientists and engineers that want to make sure that they, get to work on one of the ones that flies, or young people that are interested in sort of following in your footsteps? What is the easiest way to be in the right place at the right time?
One thing is you have to, this is sort of it feels like generic advice, but it really is true. You have to follow like what really drives you, what you're really passionate about. And for some of you, it might be engineering. For some, it might be science, like it was for me. So just finding that is important, because science and engineering are actually a lot of hard work. And if you're not really into it, it'll limit where you can go. But then also, getting experience in it as soon as possible is important. So even high school projects are great, robotics teams or science Olympiads, And then when you get to university, I think that's where it really is important to try to get experience working with a professor or a teacher that might be involved in one of these missions or give you some experience in analyzing some data for the first time. The sooner you become a scientist, the sooner you become a scientist.
So go to grad school is what I'm hearing.
Yeah.
We only have time for one more question. If you could send a new rover to another planet, which one would you choose?
Oh my gosh. Wow.
We're going to hold you to it.
Yeah. I love Mars. Mars will always be like the first place for me. But there's a lot of attention shifting now to the moons of Jupiter and Saturn because we've discovered, like with some of the spacecraft we worked on, Galileo and Cassini, we've discovered with those spacecraft that the moons of Jupiter and Saturn, some of them have these ice shells and oceans underneath. And oceans that could have more water than Earth's ocean. And so while I love Mars, and Mars may have had life in the distant past, some of these moons may still have life today. So we've never landed on like Enceladus or Europa. So I would be totally on board with getting to those planets and driving around and doing the same kinds of work we do with Curiosity.
All right, if they'll land it, you'll drive it.
Totally.
All right, everyone, please thank Dr. Ashwin.
Thank you.